Hello, my name is Pedro Cabrera. My VID ends in 87, which when added equals 15, and 1 plus 5 is 6, so I'll be doing question 6. So in part A of this problem, we are asked what happens when a positive and negative probe connected to a battery touch with each other. This spark is caused by the movement of electrons through the air between the battery terminals. In what directions are the electrons traveling through during this spark? So since electrons are negatively charged, they will always travel towards the positive terminal. So in this answer, this would be the correct one. The electrons are traveling from the negative to the positive terminals. Since electrons, like I mentioned, are negatively charged, they will travel from the negative end of the battery towards the positive one. So for part B, we're asked, on what does the electrical potential energy depend? So the formula for the electric potential energy is going to be delta UE equals charge times delta V, which is the potential difference. Therefore, since these are the only two variables within this function or this equation, it depends on the charge and the potential difference. We can see right here the choice is only the potential difference and the charge, which is these two variables right here are the only two that matter towards the electric potential energy. Moving on to part C, we're asked, assume that two of the electrons at the negative terminal have attached themselves to a nearby neutral atom. There is now a negative ion with a charge of negative 2e at the terminal. What are the electric potential and electric potential energy of the negative ion relative to the electrons? So for this problem, since the charge and the distance remains the same, the electric potential will still be the same. However, the electric potential energy is twice as much, and I'll show you why. So the formula for electric potential is V equals U over Q. Alright, we can actually rearrange this to just be U equals VQ. Therefore, now we have the charge and the electric potential next to each other. So the charge of an electron is just negative E. So we can say the electric potential energy equals negative E V. And that's pretty much that. And now, if we do it for the ion, we have Q V, which is the charge. And now since we have two electrons attached to the charge of the ion, we'll now have the electrical potential energy of the ion equals negative 2V. And since we know that U equals negative, missed the E there, negative 2eV, we can say negative EV, we can say that the electrical potential, negative 2E, can just equal 2U. Therefore, it is twice as much. So moving on to part D, we're asked, what is the electrical potential energy of an electron at a negative end of a cable relative to the positive end of the cable? In other words, assume that the electric potential of the positive terminal is 0 volts and that the negative terminal is negative 12 volts. Recall that an electron has a charge of 1.6 times 10 to the negative 19 coulombs. So to do this problem, we will rearrange the electric potential formula, which is V equals that formula right there, UE over the charge. So now this is what we want to find, so we will rearrange that as the electric potential equals the charge times the electric potential energy, electric potential difference. So we have UE equals the charge, which is 1.6 times 10 to the negative 19 coulombs, times, and since it's a potential difference, we actually have 12 volts. And when you finish this product, you will end up with 1.92 times 10 to the negative 18 joules. And that's the answer for that problem. In part E, we are asked, at a negative terminal of a battery, the electron has electric potential energy. What happens to the energy as the electron jumps from the negative to the positive terminal? And the answer is, it is converted into kinetic energy. And the reasoning behind that is because any object that has any mass in motion will eventually, and that is moving, will have kinetic energy, no matter how much mass. Since it's very little mass, it will be a small kinetic energy, but regardless, it still has some kinetic energy. In part F, we are asked, if you want to move an electron from the positive to the negative terminal of the battery, how much work, W, would you need to do to the electron? So for this, we have the equation right here, which is the charge times the potential difference, and it's the negative charge. So this is the formula to calculate the work done on the actual particle. Therefore, if we want to calculate the work that you need to push it backwards or in reverse, you'll have to flip the sign to a positive. So let's work on that. So the work is gonna equal the charge, which is 1.6 times 10 to the negative 19, and this is negative charge, that's for the actual work that the charge is doing, times the voltage, which is 12, and this will equal negative 1.92 times 10 to the negative 18. And now we have to keep in mind, in joules, we have to keep in mind that this is what the particle is doing, going in its regular flowing of motion from negative to positive. However, if we want to push it backwards from positive to negative, we have to flip the sign. So it'll be positive 1.92 times 10 to negative 18 joules. And that's how much it requires to be pushed in the opposite direction.